Imagine you're launching a rocket to Mars. You've engineered the perfect trajectory, you've got the most advanced engines on the planet, but slowly, silently, you are losing your fuel. It's not a leak. It's not a mechanical failure. It's literally just heat. Today in this explainer, we're diving into one of the most underestimated crises in deep space travel. And as you'll see, the aerospace industry is turning toward an incredibly unlikely agricultural solution to solve it.
So why exactly do rockets lose up to 80% of their fuel? Well, to understand the problem, we've got to look at what powers these massive journeys in the first place. Liquid hydrogen is widely considered the absolute ideal fuel for deep space missions. It provides the highest specific impulse, which basically means it gives you the most thrust for your buck, and it burns incredibly clean. But here's the catch. The aerospace industry calls this the boil-off crisis. Liquid hydrogen is super volatile and has to be kept at around -253 degrees Celsius. If it gets even slightly warmer, it boils, turns right into a gas, and literally has to be vented out so the tank doesn't explode. So on a 9-month journey to Mars, you could lose 60 to 80% of your starting fuel purely to evaporation. Crazy, right?
Keeping things cold in space is a total logistical nightmare. You know, in the vacuum of space, you don't have air to carry heat away. Instead, a spacecraft faces direct, blistering solar radiation on one side and the freezing void on the other. You can have the sun-facing side of a spacecraft baking at a positive 120 degrees Celsius, while just inches away inside the tank, you're desperately trying to maintain that liquid hydrogen at -253 degrees. We're talking about a thermal delta of nearly 400 degrees Celsius.
Now, you might be wondering, don't we have insulation for that? Well, we do. It's called multi-layer insulation, or MLI. These are those shiny foil-like blankets you always see wrapped around satellites. But traditional MLI fails completely on long, deep space journeys. First off, it's really heavy, adding 15 to 20% to the total mass of the fuel tank. Second, it's super fragile. A tiny micrometeorite strike can easily destroy its effectiveness. And, crucially, it degrades. Going constantly from extreme heat to extreme cold causes the layers to crack and delaminate. It simply cannot survive a 7-month journey to Mars.
So the aerospace industry desperately needs a new material. They need something ultralight, incredibly thermally resistant, and tough as nails. And believe it or not, the answer might just come from a farmer's field. Enter industrial hemp. Yes, you heard that right. Now, let's be clear here, we are talking about the non-psychoactive industrial crop. Researchers aren't looking at this plant for its botanical properties. They're looking at it as a highly engineered, ready-made biological scaffolding that nature just handed to us.
The secret here lies right in the biology. If you look at a hemp stalk under an electron microscope, you'll see this natural, microscopic porous structure. In its natural state, the ratio of void space to cell walls is 80 to 90%. I mean, it's mostly empty space. Add to that the fact that its fibers are made of high crystallinity cellulose, which happens to be the perfect foundational building block for advanced materials, and the fact that it is highly regenerative, growing in just 3 to 4 months. Nature has already built the perfect lightweight matrix. We just have to adapt it.
Of course, you can't exactly just wrap a rocket in raw plant stalks. You have to transform it. And scientists have actually developed a brilliant, almost sci-fi-sounding 3-step process to turn this humble crop into an advanced aerogel. It starts with delignification, moves to freeze-drying, and finishes up with carbonization. It's a really elegant sequence. Let's break it down.
Step 1 is all about extraction. The raw hemp stalks are bathed in a chemical solution to basically strip away everything we don't need. The lignin, the hemicellulose, the plant waxes, the whole shebang. What you're left with is a pure, flexible cellulose matrix. It's essentially the sterile, white skeleton of the plant, but with its brilliant natural architecture completely intact.
Step 2 is where the real magic happens, freeze-drying or lyophilization. The cellulose matrix is frozen and then placed in a vacuum. The ice crystals transition directly from a solid into a gas, skipping the liquid phase entirely. This replaces the liquid inside the cells with air, but without collapsing those super delicate cell walls. The resulting density of this hemp matrix is 0.02 grams per cubic centimeter. To put that into perspective, that is 7.5 times lighter than the standard synthetic NASA polyimide aerogel.
Finally, we have step 3, carbonization. This ultralight hemp sponge is heated to roughly 1,000 degrees Celsius in an environment completely free of oxygen, usually using argon gas. Because there's no oxygen, it doesn't just burn up. Instead, all the non-carbon elements basically bake away, leaving a black, pure carbon 3D network. So, you've literally transformed a plant into a highly advanced, ultra-heat-resistant carbon aerogel.
But why does this work so incredibly well in space?
Well, it all comes down to a concept called the tortuous path. I want you to imagine a microscopic 3D labyrinth of nanopores. In the vacuum of space, there's no air to transfer heat via convection. Heat can only travel as thermal photons moving directly through the structure of a material. But in this biological maze, those thermal photons get completely lost. They bounce off thousands of microscopic dead ends, scattering and trapping the thermal energy way before it can ever reach the liquid hydrogen on the other side.
And the data backing this up is just staggering. Because of that microscopic maze, the carbonized hemp aerogel blocks 97% of heat transfer in a vacuum. 97%! To put that in perspective, the standard aerospace synthetic foams currently used only block about 60 to 70%. This biological structure is significantly outperforming our absolute best lab-made synthetics.
Let's look at the ultimate showdown. When you stack standard NASA synthetic polyamide up against the new hemp carbon aerogel, the results are pretty clear. Take the thermal conductivity, and remember, lower is better here. The synthetic sits around 18 to 25 milliwatts per meter Kelvin. The hemp aerogel, a remarkably low 6 to 9. It's objectively a much better insulator. Now, consider the cost. Standard aerospace materials can run up to $1,500 per kilogram. The raw material cost for the hemp aerogel is just $15 to $30. So it's not only better, it's vastly cheaper.
But what about durability? Remember, traditional insulation cracks under extreme temperature shifts. Well, in a really dramatic lab test, researchers submerged both materials in liquid helium at a mind-numbing minus 269 degrees Celsius and then rapidly heated them in a vacuum. The synthetic NASA sample cracked and completely failed after just 3 thermal cycles. The biological hemp carbon aerogel, it survived over 50 cycles without any loss of structural integrity. It is incredibly resilient to thermal shock.
So what does this all mean? Why does this matter so much right now? Well, because launch mass is the ultimate currency of the space economy. Every single kilogram you send into low Earth orbit costs thousands of dollars, and sending it all the way to Mars costs exponentially more. If you can use an insulation that is 7 times lighter than current materials, you are saving massive amounts of weight, and that weight can be replaced with more scientific instruments, more life support, or simply more payload, literally saving millions of dollars per launch. But there's a visionary aspect to this that goes far beyond just saving money on rocket launches. It brings us to a concept called ISRU, in situ resource utilization. Basically, if we're going to build permanent bases on the Moon or Mars, we absolutely cannot rely on a supply chain that takes 7 months to arrive from Earth. Relying on Earth for replacement parts is a massive strategic vulnerability. We need to be able to make our own materials right there on the surface.
And this is the true superpower of biological materials. Think about the strategic benefits for future Martian colonists. Not only does this bioaerogel reduce the launch mass of cryogenic tanks by 30 to 40%, and not only is it highly reusable, but it can be cultivated locally. Future astronauts could literally grow their own heat shields and insulation right there in closed-loop hydroponic greenhouses. You don't need to mine heavy metals or build massive chemical refineries on Mars. You just need water, CO2, light, and a few seeds. It entirely removes our critical supply chain reliance on Earth.
Which leaves us with a fascinating final question. We're so used to thinking of space exploration in terms of titanium, aluminum, and synthetic polymers, but nature has spent millions of years engineering the perfect structures for strength, lightness, and thermal stability. Is the aerospace industry ready to truly rely on biological materials for its most critical engineering? To conquer the outer solar system, our best move might just be to take a lesson from the plants growing right under our feet. I hope you found this explainer as fascinating as I did. Keep questioning, keep learning, and I'll catch you on the next one.